The last video we have seen an example of a singular Sturm-Liouville system, comes from a legendary equation. So, we can have yet another example of a singular Sturm-Liouville system based on Bessel equation. So, we will just see what it is. You can write this example of yet another example, one more example. Okay, you can write one more example. Of singular Sturm-Liouville system. So, that is basically we take Bessel equation. So, we can have x square y double dash plus x y dash minus alpha square. Did we use alpha squares? So, alpha is square. Actually what you have is earlier plus x square minus alpha square y equal to 0. This is your Bessel equation. If you replace, you can also have modified equation, that is what I have shown, and you replace x by lambda x, what you get is the same. Okay. So, what you get is x square lambda square x square d square y by d x lambda square x square, that lambda square this lambda square cancel, these two terms will be as it is. So, you can replace lambda x by lambda x. So, you can have lambda square x square minus alpha square. So, this is also the similar Bessel equation type. Okay. Where is the domain? So, domain is for this x positive. So, for the Sturm-Liouville problem system, you should have a finite domain. Okay. That means, so what are the parameters? I brought in this parameter lambda, eigenvalue parameter lambda, and this I have already one parameter in the Bessel equation. Okay. And my domain is unbounded domain, x greater than 0. So, I have to make it a domain as finite. Okay. So, what I do is I make this domain fixed by keeping some L. I fixed it, and I fix this L, I fix this alpha, which is the Bessel parameter, and this lambda I keep as eigenvalue. Okay. So, eigenvalue parameter. So, if you do that, what happens? So, if you can rewrite fix alpha and domain 0 is only open and L. Okay. This you fix it. This is what is your domain. Domain you fix some finite quantity, L is finite. So, if I do this, what is the equation? So, equation is x square. So, you can have equation I rewrite like this. I divide with x, because x is anyway greater than 0, I can divide it. So, I can rewrite x y double dash plus I simply cancel one x both sides, I divide with x. So, you get y dash, so that these two terms I can put it as in self adjoint form, plus or minus alpha square by x into y, that is your q y, plus lambda square y into x, okay, equal to 0. This is from x between this. So, that is, you can rewrite this as p x y dash of dash, okay, minus alpha square by x y, okay, minus and plus equal to lambda square x y between x less than 0 less than L. Okay. So, What is this operator? This is like in the form Ly equal to lambda. So lambda is already lambda square, okay. So this is a kind of lambda square, okay, lambda square x into y, lambda omega y. So where lambda is, where L is, the operator L is minus d dx of x d dx plus, or rather minus here, if you put a bracket, alpha square by x. So this is your, this is like a self adjoint form. So you already have. So where P is clearly P of x is x, Q of x is what is Q of x? Minus alpha square by x, and Wx is now x, okay. So you have x. X is between 0 to L. You see that P of 0, the boundary points are 0 and L. P of 0 is 0. Since P of 0 is 0, immediately my boundary condition should be, boundary condition which I have to define as y of x, y of 0 and y dash of 0 are finite or bounded. What happens to P at L? Which is, what is P at L is L, which is non-zero. So the boundary condition should be, one of the boundary condition we can use either, what is, so you can, because this is non-zero, you can provide regular Sturm-Liouville system boundary condition, that is C1 y at L plus C2 y dash at L equal to 0, okay. So combination, or so you can choose any of these C1 and C2, not both are 0. So if not both are 0 means either C1 is 0, if C1 is 0, C2 is 0, C2 is non-zero, C2 has to be non-zero, that is you can give y dash of L is 0 or y at L 0 or a combination of them you can also give, okay. So what we do is, because with this boundary condition which I give, I take C1 equal to 1 and C2 equal to 0, that makes it y at L equal to 0, a simple regular Sturm-Liouville boundary condition, okay. You can actually take in general like this, you can choose a C1 and C2, fix your C1 and C2, make a combination and you give. But only thing is that we don't know with this boundary condition, we don't know, we didn't solve the equation. It's not easy to solve this Bessel equation, okay. But with this boundary condition we already solved, if you actually see, okay. If you look back at the orthogonal property of the Bessel functions, J alpha of x is, okay, x between 0 to L is actually satisfying this one, okay. So because we know that, well, that's why I am fixing this one. You need not fix this boundary condition, you can fix any boundary condition with for some, not both C1 and C2 are 0, some non-zero C1 and C2 you can choose and you make it 0, that you can write it here. But this we choose because we have already solved it, okay. So the eigenvalue problem is Ly equal to lambda square xy, and your boundary conditions are y0 and y dash of 0 is finite and y at L equal to 0. This is x is between 0 to L. So this is your singular Sturm-Liouville system, okay. So immediately, because W is this, what is your dot product? Dot product is integral between 0 to L. Now I have a Wx, that is x fx gx bar dx, that is your dot product, that is the definition of dot product, okay. So what are these solutions? Now we know that this is lambda is positive, lambda is real, okay. This is now this operator is in the self adjoint form, so, or skew symmetric form or Hermitian form. So this lambda is real, implies lambda is positive or lambda equal to 0, lambda is negative. So in all these three cases you can see the solutions, okay. What are the solutions we have? What are these And first of all, you consider some any L, any lambda, Ly minus lambda square, Ly minus lambda square xy equal to 0. You consider the equation, that is, what is this Ly minus lambda square y? This is actually your equation itself, that is x y double dash, okay. So that is nothing but your equation itself, okay, both are same. So you have x square y double dash, I will write this is actually x square y double dash plus x y dash plus lambda square x square minus alpha square y equal to 0. This is between 0 to L. And we know that this has solutions, okay. This has solutions that has to be bounded at 0 and at L it has to be 0. What are those boundaries? What are those values for which you have? Those are, we have seen already. So this is how we have, so the solutions of the equation, the above equation, satisfying the boundary conditions are j alpha are fixed, comma, of lambda I, okay, they are x, right, they are x. These are the solutions, these are the solutions where lambda I satisfies j alpha of lambda I L equal to 0, okay. So based on this j alpha roots, okay, this j alpha roots, based on these j alpha roots, these roots x1 x2, that is what we made, right. So you have x1 x2 x3 x4 and so on. You have infinitely many roots for the j alpha function. So you can choose your lambda 1 as xi by x1 by L, lambda 2 is x2 by L and so on, x3 lambda 3 is x3 by L and so on. So this is what you have. So all these lambda i's are nothing but roots of this j alpha divided by L. L is fixed domain, the finite number in the domain. So this is what you have. So these are the functions that you have already seen that, okay, either it is positive or negative. So basically you see only they are defined only positive side. So you have only for positive side you have these eigenvalues, okay. These are the eigenfunctions corresponding to lambda positive, because lambda when x1 x2 x3 are in the positive side, their lambdas are all positive. If lambda equal to 0 you do not have, so there is no root, j alpha will never be 0 at x equal to 0, okay. So this is not an eigenvalue, negative is also not an eigenvalue, okay. Since j alpha of x has positive roots equal to roots, if when I write equation you have to write, without equation you have to write positive zeros, and lambda i's are all positive, okay. So immediately implies eigenvalues are positive only. So this implies eigenvalues are lambda i's what are the lambda i's? So eigenvalues are lambda square actually. So lambda square. So that is lambda square, lambda I square are eigenvalues. Corresponding eigenfunctions are j alpha of lambda ix or eigenfunctions. Where is this from? I is from 1, 2, 3 onwards. This is just simply a notation. If your roots are roots of j alpha or x1, x2, x3 and so on, you can have i's index is also from 1, 2, 3 onwards. If I denote them as x0, x1, x2, then my index can have I is from 0, 1, 2 onwards, okay. So, these are simply eigenvalues and eigenfunctions directly, which we calculated already. We have already the basic groundwork we have already done while solving the Bessel equation. So, that now you are only seeing, putting in this setup and seeing that lambda I squares are eigenvalues and j alpha of lambda I x are eigenfunctions, just like Legendre case. So, immediately, so from the properties of skew symmetric or Hermitian operator L, you see that j alpha, these eigenfunctions are orthogonal and complete. Okay. From the properties, j alpha of lambda I x, I is from 1 to onwards, are complete orthogonal set. So, meaning of completeness is any piecewise continuous function f x in 0 1 can be written as a Fourier series. So, you can have a Fourier series which is I is, now I have this 1 to infinity, and you can have Cn j alpha of lambda I x, okay, where Ci's I can get it Ci, how do I get this? Take a dot product. So, dot product with this f with this eigenfunctions j alpha of lambda I x, which is equal to Ci integral, this is also dot product, which is j alpha of lambda I x with j alpha of lambda I x. What is this dot product? Integral minus 0 to L x f x j alpha of lambda I x dx. J alphas are all real valued functions. So, bar is immaterial. So, you have Ci integral 0 to L x into j alpha of lambda I x, this square dx. Okay. So, we know already what this is. Okay. We just calculated look back earlier properties of Bessel functions, we know this value. Okay. So, by using this you can get your Ci's finally, where this is what is the Fourier series, with these are the Fourier coefficients as I. So, I can write Ci as 0 to L x f x j alpha of lambda I x dx divided by this integral value L square by 2 j alpha plus 1 of lambda I L. Okay. Or it has the values, this is actually equal to Ci times L square by 2 j alpha plus 1 of lambda I L, or Ci times L square by 2 j alpha minus 1 of lambda I L, both are same. Okay. Either this or this, both are same. So, you can use any one of them. Okay. Either this or 0 to L x f x j alpha of lambda I x dx divided by, so you have a 2 goes up, 2 by L square divided by this integral. So, 2 by L square, this divided by j alpha minus 1 of L lambda I into L. So, these are your Fourier coefficients, I is from 1 to onwards, 1 to 3 onwards. So, these are your Fourier transforms, and these are your Fourier series. Okay. So, this is the Bessel Fourier series. Bessel Fourier transform. Okay. So, these are so you can have like this, you can have many Fourier series. Okay. You can break the time signal into in terms of these orthogonal functions, complete orthogonal functions j alpha of lambda I x. I is running from 1 to infinity. Instead of sines and cosines, and have get back your signal in terms of these orthogonal functions as a discrete sum. So, that is 1 to infinity, take a linear combination of these at discrete frequencies. If you add them up, you can get back your signal. So, this is what you can get. So, these are the only two examples we do for this singular Sturm-Liouville system. You can pick up many things, but only thing is you have to do the groundwork to solve, to find the eigenvalues and eigenfunctions. That involves a lot of work to find these solutions. For example, if you consider Hermite equation, you can get Hermite polynomials. Okay, they form complete set and get your Hermite Fourier series and so on like that. Legendre log array polynomials. These are all the special equations, special functions or eigenfunctions. With that, you can get your Fourier series. So, a periodic system is unique, which you have done mostly general setup, which between the domain A to B, and we have seen only one example for the regular Sturm-Liouville system. So, we will have one more example for the regular Sturm-Liouville system. We can solve, we can try to find the eigenvalues and eigenfunctions. A special type of regular Sturm-Liouville system. Okay, so an example of regular Sturm-Liouville system. Benjamin, இது போதுமா? இது எவ்வளவு வந்தது?
23 minutes வந்தது சார்.
23 தானா?
இது இன்னும் 10 minutes போகுமா?
10 minutes போனா இது ரொம்ப அதிகமாகும். ஸ்டாப் பண்ணலாம்ல? Okay, so we have this example of regular Sturm-Liouville system. We will do this now. So, we have equations are y double dash minus 2y dash plus lambda y equal to 0 and x is between 0 to pi. Let us take this, and because regular Sturm-Liouville system, you see that coefficient of y double dash is non-zero. So, that means you can expect p of x is non-zero at those endpoints 0 and pi. So, the boundary conditions I give, it is given that these are y pi is 0. Let's take the simpler boundary conditions. These are the boundary conditions. So, we will try to find eigenvalues. So, basically the problem is to find the eigenvalues and eigenfunctions for the regular SL system. This, okay. So, we will try to find these eigenvalues and eigenfunctions just like what we had earlier for the regular Sturm-Liouville system. Only difference is you will not be having explicit eigenvalues. You may have to denote them, okay, based on some equation that is called dispersion equation. So, we will see this example, how to get these eigenvalues and eigenfunctions, okay, that we will see in the next video. Thank you for watching.